Hello, today I will continue to talk about network compression and acceleration, and today's topic is front-end compression. First, I will introduce knowledge distillation. It is the process of transferring knowledge from a large model, a teacher model, to a smaller one, which is a student model. So there are two models. One is teacher model, which is usually a big and powerful model. It has been trained well, and the other one is a student model. It is usually small and fast. Every time we receive a batch of data, the student and teacher predict this data independently, and we want the predictions of these two models to be as similar as possible. We consider the teacher's prediction as a supervision and compute the prediction loss between the teacher and the student. The supervised loss could be many types, including probabilistic distribution, output feature, middle layer feature map, attention map, or middle process. Now let's take a look at an example. Here it uses the probability distribution, which utilizes KL divergence loss in this example. KL divergence is a measure of how one probability distribution is different from a second one, reference probability distribution. It is asymmetrical, and it uses DPQ to show the distribution Q to simulate the real distribution P. This picture explains the KL divergence. Here, network theta 1 is the teacher model and theta 2 is the student model. Now there is a batch of training images. Both network 1 and network 2 will make a prediction to these images. P1 is the prediction of the teacher and P2 is the prediction of the student, and I use them to calculate the KL divergence. The final loss for the student will be the classification loss and the KL divergence loss from the teacher's prediction. PyTorch has an API for KL divergence loss. Size average meaning if we want to divide the loss by the dimension number, and I define a loss that uses KL divergence. And L equals to the loss between student probability and the teacher probability, and then divided by batch size. The second type is feature map. An input image is fed into both the teacher network and the student network, and we could get some feature maps after these two networks. We want the feature maps to be as similar as possible between the teacher and the student. The easiest way is to use L2 loss to calculate, but it's quite brute force, not very elegant. A more elegant way is to calculate the MMD loss. It tries to make two domains more similar. For example, the blue one is a student and the red one is a teacher. They belong to two domains. And after MMD loss, those two feature maps will belong to the same domain. If we use L2 loss, the blue circle and the right triangles will be overlapped. But MMD loss is more mild. Could I use middle process to calculate loss? Yes, we could. When an image is fed into a network, it could produce many feature maps in the middle process. I used the Fsp method to calculate loss. Fsp is to use the gram metric to encode the feature map flow. And we encode both the teacher feature map flow and the student feature map flow. We try to make those two as similar as possible. So we calculate the L2 loss of two gram matrices. The full pipeline is like this. The teacher network has 32 layers and the student network has 14 layers. Both of them are separated into three parts. Each part we could calculate a gram matrix, and they should be as similar as possible. This is the idea of knowledge distillation. The teacher's information is used as the supervision to train the student model. And another front-end compression method is to use compact network design. We could use ShuffleNet, MobileNet v1, v2, SqueezeNet. We have introduced them in the previous videos. SqueezeNet idea is to use 1-1 filter, reduce the number of input channels, and change the downsampling. MobileNet v1, its main idea is to use depthwise conv plus pointwise conv. MobileNet v2 uses the inverted residual blocks. ShuffleNet is similar to MobileNet v1. It uses depthwise conv, but instead of using pointwise conv, it uses ShuffleNet channel shuffle to connect different channels information. This is SqueezeNet. I have introduced it before. The main idea of it is to use 1-1-conf to reduce the number of input channels, and they also use 1-1-conf to replace some 3x3-conf. Also reduce some pooling to keep the feature maps. And these are some SqueezeNet architectures. MobileNet v1, we have also introduced it before. It mainly uses 3x3 depth-wise and 1x1 point-wise conf. Let's talk about MobileNet v2. It is an improved version of MobileNet v1. It adds a point-wise conf before the 3x3 depth-wise conf, but this is not the first time to add point-wise conf before depth-wise. SqueezeNet also does so, but interestingly, MobileNet v2 uses this 1-1 point-wise not to reduce the input channels. On the contrary, it is to increase the input channels. And v2 also erases the second point-wise activation function so as to not lose feature information, as ReLU will throw away the negative numbers in the feature map. Instead of using ReLU, it directly uses linear. It means that there is no activation function. v2 also uses shortcut structure in ResNet. If we only see one block, v2 actually increases the number of parameters. But one block is more informative for v2 because it increases the number of input channels, also uses the shortcut, so each block is more shallower compared with v1. The last layer is only 320, and this 320 is actually used by conf. And before this 1-1 conf, the widest width is only 160. So v2 compresses 50% parameters compared with v1, and it is easier to generalize. And ShuffleNet, we have also introduced it before. It uses channel shuffling to replace 1-1 pointwise conf because MobileNet has 90% parameters and 75% flops for pointwise conf. If we could get rid of 1-1 pointwise conf, the model could be much more compact.